So thoughts, did you guys come up with something? You guys were talking, that's good. Talking, dialogue, sharing ideas is always good.
I said how in this case, when you multiply the rate to the number of hours, it would give you the distance between the car but to Phoenix.
Okay.
And what we're looking for is y, but we were unsure if it would be represented as dy because it's the change in that.
Okay. So you're bringing up dy. Okay. So the task was to embellish this drawing with y and things relative to y. So did you do that? Do you know what I mean by that? We're going to add more detail to the drawing. Add something to it. Draw more so that it's relative to the value of y. Yeah. Yeah, go ahead, Lydia.
You could like make a line
Yeah.
that's decreasing with the dy from LA to the car.
From LA to the car. So from LA to the car would be what quantity? Dy. She wants dy. What do you think?
Like if you put it changing, it could be like a fixed distance.
All right, so are you imagining something like this? So can you see the difference in the colors there? Do you see blue, pink, and black? So which color were you talking about, Lydia? Which one? Black. So the black, the length of the black bar is dy. Agree with that? Or these two are shaking your head. Why not?
I think it's y.
I think it's y.
Distance from LA.
Y. So y is defined as the distance from LA. So she's proposing the black bar should be y, not dy.
I think because it was represented y is Los Angeles to car, but in this situation, since MX gives you car to Phoenix, that change in y, I feel like you just have to add it on to the distance of Phoenix, right?
So what do you think the black bar is? Yeah, so those are all good. It's all good, reflection. What do you think the quantity for the black bar is? She's saying dy. Are you staying with dy? Yeah. You're staying with dy, and over here they're saying y. So what do you think, Jason?
I think
I think it's y. What do you guys think? Y. So if y is the distance from the car to LA, is this the distance from the car to LA? From here, the length of the black bar. It is, isn't it? Yeah, it's a variable. Yeah, variables vary. Yeah, it's awesome, right? It's changing. Variables vary. Now I could pause it. You have to pause it in your picture. You have to, you can't draw the thing changing. I can do the animation. But yeah, variables vary. X is taking on many different values. And then as X takes on values, Y takes on different values. Function, right? Cool. All right, so now that I've given you this, can you finish the picture? So I think we agree that the black distance is y. So what about the others? What might we use to symbolize the blue and is it pink? The pinkish. Talk about it. What do you think? So like I said, on your paper, you're just gonna have something like this. You're just gonna have like one particular case. Nice thing about animations, we can take it to the next level and model it as a changing situation. But when you sketch it, you're just gonna have like this thing paused somewhere. Okay, come on, let's go ahead. I'll just go ahead and pause it now. So we're thinking that's y. So what do you notice about the blue bar? Constant, right? So what kind of thing is it here? So it's like a parameter, right? So what parameter is it relative to y? He wants y initial. Is it a particular y? Is it a particular distance from the car to Phoenix? Yeah, the one at 3 hours. So we can call that y initial. Whoa. Okay, so what about the pink? dy. Is the pink dy? Agree. You agree with that? Okay, good. Okay, what did we say dy was? Just in terms of y, so not in terms of x. But what would you say dy is? Yeah, so the change in a quantity is y final minus y initial, right? Isn't that what we've said before? Okay, what about in this picture? If you were just looking at this picture, what relationship would you build out of this picture? So looking if you didn't know anything about, dy or what, just purely geometry, what about,
Negative dy.
what's that?
A negative.
But what relationship would you have for this picture right here? Yeah, doesn't it look like y plus dy equals y initial? You see that? If you add those two distances together, you always get y initial. All right, so let's write that down. All right, so that means dy, and then so we can think of this varying y as kind of like the final y, right? If we were to pause it, then y would be like y final, kind of, okay? So then from that, we could say dy equals y initial minus y, which is like y final. Are those correct? Are they the same? So what's the problem? Right, now we're getting, in this picture, it seems like it should be y initial minus y final, but we know that the variation in the quantity is y final minus y initial, so where are we going wrong here? Alyssa knows. Winston knows. What's the problem? There's got to be some assumption we're making that's incorrect.
That dy is going to be positive.
Is dy positive?
No, because if you do it that way,
Okay, but so don't reason with the equations, reason with the situation, right? Is dy positive or negative? Okay. So from the starting value of y here to this value of y, how much did y change? Yeah, do you see that it went down? So the change was less than 0, right? So y was this value, whatever this is, say, I don't know, say 250 miles. And then now y is, 180 miles. So y decreased. See that? So dy is less than 0. So if dy is less than 0, then does this make sense? Is it y final minus y initial would give us dy, because then you have a negative value because y final is less than y initial. So this assumption was incorrect, because this is assuming that dy is a positive quantity, right? Adding these two positive quantities together gives you that. That's not right. Okay, cool. So so this is an example of a decreasing, our dependent quantity is decreasing, and this is showing as a length on the picture, it's showing it getting bigger, but we know that that's getting bigger negative, right? That's getting bigger negative. And not just because it's going to the left, right? It's not because it's going to the left. It's because the value of y is decreasing. Okay? Very good. So I've got some here's the value of x and y, and I'm showing them. So this is x is now at 3 hours, 4 hours, and then the corresponding distance from the car to LA. Now 100 miles. So the picture might not match up with proportionally to the values, but just pretend that those values in the picture are correct. So my question is, based on watching x and y change together, right? Watching x and y change together, is y in a constant rate of change relationship with x? Is y changing at a constant rate with respect to x? Discuss. What do you think? Looking at those variables change. So you think yes or no, and you give your reasoning, and we're talking out loud at your tables. Go. Let's just skip to the next part. I'm going to show you the ratio of, so this is now calculating at any moment, based on the values of x and y, it's calculating the ratio of y to x. And then this is this is not like derivative, it's truly calculating this divided by this at every moment. Okay, so this is a computation, it's a quotient, as is this. And based on these four values, it's telling you the current value of each ratio or quotient. So, ask again, is y changing at a constant rate with respect to x? What she said makes sense? Okay. All right, so now I want to actually graph this in the coordinates x and y as they change together. So I'm going to come over here. So I don't know, have we done that yet? Opened up a second graph window? So to do that, to open up a second graph window, so I'm going to do Control 2. I'm going to graph a point. So to plot something in another window, you use apostrophe. And it's a little confusing because that looks like prime, like derivative, but it's not. It's GC's way of graphing in a second window pane. So apostrophe does not mean prime. It means graph on a second coordinate axis. And so what do I want to graph on that second coordinate axis? I want to graph capital X and capital Y. Those are quantities in the problem. So you see when you introduce x prime or y prime, it opens up a second window over here. And then if I graph, 2 points. Oh, the car is red, so let's go with red. Okay. It's not letting me graph. What's wrong here? It's not happy. Oh, there's the point. Oh, it is graphed. Okay. So then here, now I'm showing you just the time since leaving Phoenix here. All right, I really should write out since leaving Phoenix, but I don't have room for that. So X hours. And then this is our Y. And it's our distance to LA. Miles. Okay, so now I'm showing you how those, I'm showing you on the coordinate plane, how the X and Y change together. Question? So this red point is showing, it's showing what? It's showing the value of X and the corresponding value of Y, graphed as a coordinate pair, right? So there's lots of points, right? So there's lots of them. If we were to graph them all, and Y was at a constant rate of change with respect to X, what would be true? I'm asking a visual question. To represent all those points at once rather than one at a time. Would it be a straight line? Yeah, right? So yeah, it'd be linear. What is it? Yeah, so you're good. Y is at a constant rate with respect to X? Y is changing? Yeah? What do you think, Alyssa? I think so. All right, so the point is that, so I said before that this is kind of similar to Y equals KX. Is that the test for constant rate of change? Why not?
Because, okay, so X and Y would mean like one, okay, so that'd be like one time to one distance.
Okay.
And in order for you to see the constant rate,
Yeah.
you have to see like where that one time is to another time. And then from where you are now to where you were before. And so that would constitute like how fast you factor it.
Okay. It sounds like you're talking about the change. You're talking about changes, right? Like the one time and then a time later. All right. What about this? Is this the check for constant rate of change? But between what? Is this the check for constant rate of change between dy and dx, or is it the check for constant rate of change between y and x? Yeah, right? So this is checking to see if y and x, if this holds, where k is a constant, that's showing that y and x are in a constant rate of change relationship. Not that dy and dx are in a constant rate of change. They are, but this is the test or the underlying principle behind y and x being in a constant rate of change. So instead of y equals kx, so this is not right, right? This is not a valid test for constant rate of change. But what would be? What would be a valid test for constant rate of change? Okay. So that goes back to this, but yeah, so that goes back to dy equals k dx. Yeah, exactly. Yeah, that's good. So no, that's actually. So if you had some initial point, this would be the check, right? That for any point, then and some initial point, you'd have this relationship. So it's not this. It's this. Okay, so now I want to show you and when this is true, so we're talking about linear relationship, right? So I want to teach you a different way than, so when you hear linear relationships, calculational perspective would go right to what? You think, so in terms of lines and, that, no, so like if you think of high school students, junior high students learning lines, calculational perspective, what is it all about? Mx plus b, right? Mx plus b, okay? So I'm going to show you something that's a lot, rather than mx plus b, solving for the y-intercept, finding the slope, solving for the y-intercept, got the equation of the line. So I want to show you something, a way of understanding lines, linear relationships, that's in line with our understanding of uses constant rate of change. So here's what we're going to do. And so my experience is that this does not come quickly. You're gonna watch me, and you're gonna be like, oh yeah, sure, and then I'm gonna ask you to do it, and you're gonna be clueless. Okay, so just really try to zone in, and really hone in, and be in the mode of, hey, I want to retain this, like I want to learn this. Okay, because it's year after year, it doesn't come easily. Okay, so here we go. So we're gonna start with some initial point here. So make it easy. 3.5 and 252, okay? So initial point, 3.5 hours and 252 miles. In fact, I'm gonna actually graph that point so I can use this one for a different thing. So I'm gonna and I want to actually just graph straight up, graph 3.5, 252. Okay, and so then some time goes by, and it could be any amount of time. And so this is some later time, and now the current distance from LA. So here's what we're going to do. The first thing we're going to do is, so what comes first? Change in time or change in distance? Yeah, like we think of independent variable, right? So we think about for some change in time, right? For some change in time. So we're gonna, and we've kind of done this before. I'm gonna sketch, right? Black. So how do I show the change in time? All right, and so this is any xy. It's not necessarily the one that's being shown, whatever that number is in 144. It's just any value of xy, okay? So I'm going to show the change in time starting at 3.5 hours to any other time. And we've done this before, right? We've, in several assignments, we've shown that change in the independent variable as, but shown it. How do we represent it, though? Horizontal segment, right? Horizontal segment. Okay, so that's my dx. And what does dx equal? In this case. What's that? Okay, so, but you're saying 3.5 plus dx equals, that equals x, right? So then what would dx equal? Final minus initial, right? X minus 0.35, or 3.5. See that? So we're going to start with some change in time, some variation in time starting from 3.5 hours. And then variation in time will be x minus 3.5 for some final new point. Okay? And then when you have a variation in x, then what else do you have? Variation y. How am I going to show that? Vertical segment. Okay? And I want to write what dy is. So dy equals, rather than Rather than y final minus y initial, I want to use constant rate of change now. I want to force this to be constant rate of change, right? M dx, right? What's our m? Negative 57. And what was our dx? Right? So what came first? Define dx, right? Independent variable comes first. So we have a change in x, and that's any final time minus our starting initial time, x minus 3.5. And then second, we get dy, but we use constant. We're going to say this is a constant rate of change. So we're going to use constant rate of change. So dy equals m dx. We're going to do m minus 57 times x minus 3.5. Okay? And so then writing every point on this line is really defining what y is. And this is kind of like y final, right? So y final is what? How do I get a final value of y? Remember?
Y initial plus
Yeah. Plus?
y.
Good. And my y final in this case is just all possible values of y, right? This is a variable point. Okay, so I'm going to write y. What's my y initial? 252. And what's my dy? Minus 57. What? X minus 3.5. So what did I just found? I just found all possible, given any new time since leaving Phoenix. This tells me the corresponding distance to LA. Okay, and so then if I come in here and I come up here, and I'm gonna, so if I do y, and I want it in the new graph, right? New graph, so y apostrophe equals 252 plus negative 57 times x minus 3.5, x apostrophe. So what does GC do? It graphs, you give it a set of points, and it shows you the set of points. So what set of points will that be? But let's restrict it here. So what do we want to show? Well, how have we done this before? So what would be logical?
3.5 greater than x.
So just because we had an initial point of 3.5, were there points for previous times? Yeah. So I'm kind of picking this point in the middle of the trip, but we still can show points for earlier times. 0 less than x apostrophe. Oh, and sure, that's cool. So then it'll kind of generate it as we go. That works. All right, so then here we go. So now this is showing all possible points, correspondence of time since leaving Phoenix, and just fix it there. So what's better about this than y equals mx plus b? Okay. Yeah. Right. So it's the equation that we get retains the meanings in the actual problem. Good. What else? It's really good.
It covers all points and not just
Okay. Maybe instead of saying what's better about this, like what's worse about y equals mx plus b? What's a disadvantage to y equals mx plus b? Suppose our trip was like this. Suppose that our trip was this was the real graph of time and distance. And then at 3.5 hours is when we started at a constant rate. What about y equals mx plus b?
We can't calculate change.
Okay. But what about this is not, what's the problem with that?
It wouldn't show the difference at the start that it was before it was like the
Well,
constellation.
So this would be showing what's the value of b?
The y point.
Yeah, it would be this y-intercept up here. And tell me about this y-intercept in this situation. Yeah, right. It's like meaningless, right? You see that? So if you were to do y equals mx plus b, then that b value would have no relevance in the situation because you're really truly starting at your constant rate at 3.5 hours. So then this where y is or what the distance is when x is 0 is not correct and irrelevant. But what about in this equation for that situation? Yeah, if you define x to be greater than 3.5, then everything is still relevant in that. Do you see that? Our starting distance, our constant rate of change, and our starting time. Another great thing about this, not only does it show the meaning of the situation, but it shows what? It shows our change in x. It shows that dy equals mdx. And it shows that y final is y initial plus the change in y. So you see all three steps that we did to get there, which are all important concepts. They're all right there embodied in that equation. Okay, any questions? So let's practice. You guys practice. Let's go back to the let's practice on the laptop battery situation. Okay, so your goal is to, let's see, based on the point, that's 35 minutes into class. So this is at 35 minutes into class. There's 41% of your laptop battery remaining. So based on that initial point, I want you to build the relationship of battery life to time, right? Battery life to time in class. So show all the steps. Think through and write down all the steps in between. See if you can do it. We want the relationship between percent left and percent left on your laptop and time since class started. You're building the mathematical relationship of number of hours or number of minutes since class began. And percent battery percent. So that's two quantities. They're in a relationship. I want you to write the mathematical relationship, but build it up from scratch.
What's that when
When
I was
you-
asking about the,
Yeah, you're asking about the question, yeah.
the random point?
Yeah.
We were just going from
So we're gonna go from here to here? No. Instead?
to any point.
Any point, right? So you could use this triangle I got here. So any point is called
X1.
xy. So that's like kind of like step 0. We're representing every point, right? Every point in this relationship between x and y, or number of minutes since class started and percent of battery. Okay, step 1. What do we do first? What comes first? dx. Tell me, Veronica. X minus 35. So what is this saying? The variation in time starting from 35 minutes to any time, x is x minus 35. Okay. How about Lydia from there? What's next? So this is our x dx is x minus 35. Y final minus y initial? However we want it. Yeah, we want to use constant rate of change. Oh, so it's, I think it was negative 0.325 or something? Times? X minus 35. Okay. And then Astrid, what's next? Okay, I'm just going to right to it. So y final is, right, every y final, right? Every single y final equals 41. Okay, so this is what we want to learn, right? So yes, there are formulas involved, but the formulas all have meaning, right? The variation in the quantity is final minus initial, and that for constant rate of change, our variation in dependent is the rate times the variation in independent, or dy equals mdx, and then this other important thing that the final value of quantity is the initial plus the change, right? So we use all those important concepts that are the meanings behind these formulas to get our this is big people's equation of the line. But more than just equation of the line, it's showing what? It's showing all correspondence points of two quantities, right? When you have a constant rate of change relationship. So all correspondence points of two quantities, dx and dy? Is that what we're talking about the two quantities? It's talking about how dx and dy are in constant rate of change? X and Y, right? So all corresponds to two quantities. In this case, number of minutes since class started and percent of battery remaining. So rather than y equals mx plus b, we're using y final equals y initial plus change in y. And rather than talking about the equation of a line, we see it and think of it as, oh, that's giving me all correspondence points between two quantities in a constant rate of change relationship. So now I can for any value of x, time since class started, this relationship will tell me what the corresponding battery life is, right? Okay, and this is much, much more relevant for calculus. This is like, it's using all the underpinnings of calculus, as we'll see, which mx plus b just becomes kind of like, you know, standalone kind of exercise. Monkey see, monkey do, okay? All right, any questions? Okay, how did the region problem go? So so we'll have the second assessment. It's today, Thursday? Either Tuesday or Thursday. I have to look and see if we have anything more to cover for the second assessment. So I'll post it this afternoon. It'll either be Tuesday or next Thursday. But how did the what was the journey of your thinking and the journey of your emotions working on this problem? What was that called?
The region.
Yeah.
Well, I identified that you would need like two different lines.
Okay, so let's just hold on. Let's see. I get this fast.
But what threw me off is like I didn't know that the other line would cut off this line where they intersect.
Okay. So you found the equation of this line. Okay. So here might be a good place to use y equals mx plus b. We're not really talking about, this isn't really quantitative analysis. We're just trying to graph this set of points. We're given the y-intercept. So here's a situation where y equals mx plus b might be appropriate to write down that equation quickly. But when you're talking about the relationship of two quantities that are in constant rate of change, now you're talking about what we developed today in class. But so this one is y equals, what is it? 1/2 x plus -2 or -2. Okay. What about the other one? So then you said you didn't realize at first, but that you have another line, right, that you could use. So what's that? This is -3/2, the slope? Like that? Okay, so we got the two lines. So then, is that kind of what you did in your solving process? You found the two lines, and then how are we going to use those two lines now to specify this set of points, right? GC is all about show me the math for a set of points, and I'll graph the set of points. That's what GC says. I'll graph the set of points that you tell me. So, how do we get from those two lines to the set of points? Lydia, did you? Okay, greater than this one? Less than for the other one. So is that two different math lines? Oh, you did a comma between them. Does that work? Oh, okay. Didn't know that. Didn't know that would work. So you said y is greater than 1/2 x minus 2, comma, and y is less than. Did I get it wrong? This is 2/3?
Yeah.
Oh, okay. y is less than minus 2/3 x plus 1. And then you can do, so color is a built-in thing, and so like you get like a whole rainbow, a continuous rainbow of colors from 0 to 1. So if I just can come in here and say color equals 0.42, that's some color. We're going to find out what color it is. It's a very trendy green. So then what you can do is you can say color equals C, and then on a new line you can say C equals slider from 0 to 1. And then as you vary C from 0 to 1, you get all of these possible colors. So when you're
tell you like, okay, so let's say I find a cool color, like
yeah.
you go to the slider and say,
Yes, I just have to, yes, it's over here, it tells you the value. Yep, so you find a color that you like, then you use that constant. So in there, so I had something like this when I gave you the image, something like 0.5 or 0.55. But that green was nice. Okay, so two things. So we're talking about regions, and we're also talking about how constant rate of change now gives us linear relationships, right? So we're kind of doing two things at once here. So there's a homework, another homework they have for Tuesday, which will be. Oh, we got 2 minutes. So how would so this was one way to graph a region, kind of thinking about like vertically all the points less than one y value and greater than another y value. So then obviously you could get horizontally would be a matter of what? If we wanted to say left of this and right of this, to be your x. But what about like if I had a circle and I wanted to shade inside of a circle. So that's different, right? That's different than. Okay, so what's the equation of a circle? So if I wanted the center to be, say, at 2, 4, so and with a radius of if the radius was 1.5, then what would I put here? 1.5 squared, right? Okay, so that's just the points on the circle, right? So this is you've learned this before. This is the equation of a circle, and that's just the points on the circle. So suppose I wanted to plot all the points inside of that, or say outside of that circle. I want to plot all the points outside of that circle. Okay, so would that make sense? We're talking about all points, right? All points x and y that are what? So that this is like the radius squared, right? So then this would be the radius squared would be greater than 1.5 squared. So we graph everything outside. Does that make sense? Let's just leave it at that. All right, so if I change this to greater than, what am I going to see? A whole lot of blue, right? So here's another way to shade. So there's the basic way of shading where, and then, so maybe a little bit cleaner would be to do this, you know how to do this without the comma? So put the least one first, less than y, less than, yeah, okay. So then, we got, you can put, you can shade between graphs based on their y value. You could shade between some kind of vertical functions based on x values, but then you can also shade in or out of a circle based on radius, right? All points greater than the radius, all points less than the radius.